computer off. Aha, so it's...
I'm the host now.
You're the host, okay. Well, you're on the same Wi-Fi that I was on.
No, I have my hotspot.
You have a hotspot. Okay, very good. Thank you. Thank you very much. Please spotlight 306. Yeah, okay, because then the video will get that. Okay. If you manage to record it. Okay, so we're mainly going to look at what's special about categories of algebras, and I'm going to have three main running examples through the lecture, and these running examples are going to be used to illustrate general and powerful theorems in category theory that I will apply to those main examples. So the first example is one about old friends, which is the category of groups. There's not much more to say about this, so I won't, except that it's going to be one of our examples. It could be any other category of similar kinds of algebraic structures like rings or modules or something like that. So I'll just summarize and the relevant bits for today. So we have the forgetful functor that maps a group to a set, to its underlying set. And as we saw 2 lectures ago, and I won't bother to write the diagrams down again, U has a left adjoint. So F from set to group. And this is the free group functor over a set. So we call this the free group functor. And if you've done some group theory, you may know you can construct the free group by, you construct a group, you take all the elements, you're building a free group over a set X, you take the elements of X as generators, as it's called, for the group that the free group that you're constructing. You then form words whose elements are these generators together with inverse elements for the generators, words out of those, and then you put some equivalence relation on those, identifying those words that would need to be the same in the free group. And then that quotient set from the set X is the free group over the set X. So we can perfectly well do that, and a similar construction works for any kind of to give free algebras for any kind of algebra that's, say, simply described by some operations of fixed arities and some equations between them, just like groups. So we have the explicit constructions of such adjoints. Saunders Maclean, in his book Categories for the Working Mathematician, calls such constructions fussy. They're a bit fiddly. You don't want, in mathematical practice, it's quite useful to have a free group. You don't often need to know exactly how it's constructed. So one of the things we're going to do today is find out how to find such adjoints without constructing them explicitly. In this case, it doesn't really matter because we know how to construct one explicitly, but in other cases, it's not so easy to construct an adjoint explicitly. So that's the first of our example categories. The second one is going to be a category of partial orders. And I think people give it different names, but I'm going to call it CSL, which stands for complete semi-lattices. So what is a complete semilattice? Well, a complete semilattice or CSL for short, just use lowercase, that CSL underlined in capitals is the name for the category, is a partial order, a partially ordered set, So set together with a partial order on it that enjoys the property that it's complete. And what complete means is every subset of elements has a supremum, or another word for supremum is least upper bound. A smallest element above that's an upper bound for them. I hope that everybody knows what supremum or least upper bound means. If you don't, we can explain it in one very quickly using category theoretic terminology. This, the least upper bound of a subset of X is the co-product of those elements in this partial order considered as a category. That maybe doesn't make it easier to understand than the order theoretic definition. So it's a partially ordered set for which every subset a subset of X has a supremum. Which we'll write like this. It looks like a V, but it's actually a in LaTeX it would be / big V V double E. It's kind of a, you know, like a join or something. So as it's a co-product, it's determined up to isomorphism, and isomorphism in a partial order is just equality. So basically, a complete semilattice is a partial order that has a property that for any set, this unique supremum exists. Particular case of a subset, sorry, this should be the subset. This should be the supremum of A. A particular case of a subset is the empty set. So the supremum of the empty set is the least element. So in particular, X has a least element. Namely, the supremum of the empty set. But more interestingly, if you've got a partial order, we have the notion of least upper bound or supremum. There's a dual notion of greatest lower bound or infimum or infimum. Never quite sure how to pronounce it. And it turns out if every subset has a least upper bound, then it's also the case that every subset has a greatest lower bound. So it follows, let's put this in a different color. It follows that every subset has an infimum. And the proof of this is not difficult. It's a nice exercise for you to do if you've not seen this before. You simply define the infimum as, so that's the greatest lower bound as the supremum of all lower bounds. And then you prove that that is indeed a greatest lower bound. So this means that a complete semilattice, we've defined it as a partial order that has arbitrary joins or supreme. Another word for supremum is join or suprema. It also has arbitrary, it follows that it has arbitrary meets or infimum or greatest lower bound. And such a structure is called a complete lattice. So that is every complete semilattice is a complete lattice. So in a sense, there's no difference between the notion of complete lattice and complete semilattice. So why am I calling the category complete semilattices? Why use the word that has more syllables than it has to have? And the reason for this is because it does make a difference when you choose the morphism between what morphisms you take between these structures. So I'm going to take as morphisms or homomorphisms those functions that preserve the order and preserve just the suprema. So a morphism, maybe I'll call it morphism of CSLs is a function. So from
It's a bit loose.
okay, thank you. So because is that better? So morphism of CSLs from one complete semilattice to another x prime, say, is a function f from x to x prime that preserves the supremum operation. So such that for all subsets A of x, if we apply f to the supremum of A, that's the same thing as taking, so this is the supremum of A in x, of course. This is the same thing as taking the supremum in x prime of the set we get by applying f to every element of A. In other words, the direct image of A under f. Which I just write like that. It follows from this preserving supremum, a little exercise, it follows that such a function preserves also the order, is an increasing function. It also follows that it preserves the least element, but it does not follow, even though both these partial orders also, because they're complete semilattices, they're also complete lattices, so they have arbitrary infima. It does not follow that the function preserves these infima. Okay, so that's why we're calling the category complete semilattices, because it's the functions that just preserve suprema. Going back to the category theoretic way of looking at things, a partial order is a category in which there's only one morphism between any two objects, and the only isomorphisms are the identities. We saw that in the first lecture. A complete semilattice is a partial order is a category that is co-complete. It has arbitrary colimits. The suprema are co-products. Any partial order trivially has co-equalizers. So think about that. So the complete semilattices are co-complete, small partial orders that are co-complete, and the morphisms are exactly the functions that preserve colimits. That's a category theoretic way of looking at things. But we can look at it easily as sort of, we have here a category, CSL, of complete semilattices of ordered structures and morphisms between them, order preserving functions that preserve these suprema. But maybe what's not so obvious, so this is not quite, it doesn't quite look like a category of algebras, in that an algebra is a set with some structure imposed on it. Here we're dealing instead with a category of partial orders, and we're not imposing structure on the partial orders, we're saying partial orders with a property. Having the suprema is a property, it's not structure. When it has suprema, they're uniquely defined. But nonetheless, one can view this category as a category of algebras and homomorphisms between them. So I want to now elaborate that. And it's not very hard in this case. Let's see how. I've got it in the notes. So an alternative formulation. We want to view, instead of viewing it as partial orders with a property, we want to view it as sets with some operations on it. And the morphisms are going to be functions that are homomorphisms, so namely preserving the operations. So the alternative formulation is a CSL is a set X together with an operation which I'll use this join operation for, because it's going to be the join. And this operation is not unlike the usual algebras like groups, where our operations all have a fixed arity. This sort of has a varying arity, but in the sense that the arguments to this operation are subsets of the set. So we view the domain of the operations of the power set of X, and so given this, so it's an operation that to any subset of X assigns an element of X. And of course, this is going to be the join operation in the complete partial order. Satisfying just two equations suffice to give us exactly the same category as the category of complete semi-lattices. So satisfying two equations. The first one's a very simple equation, but if we take the join operation, as we'll call it, and we apply it to the singleton set, we get back the element to any singleton set, we get back the element X. So this is all elements X of the set X. And the second one is less simple. And this is that if we take a family of subsets of X, let's call it curly A, and we take let's see how I've written it in the notes. Then taking so we're going to say for all curly A, this is a family of subsets of X. So that's an element, that's a family of subsets of X is a subset of our set of X. And we're going to say that if we consider the join of what we get we've got a family of subsets of X. So for every subset, we can take the join of that. So we take the join of B for every subset B belonging to the family curly A. And then once we've got the join for all those inner subsets, we take the join of all the joins. That's the same thing as what we get by taking the join of the single subset we get from unioning together all the subsets in A. So the join applied to the union operation of A. So this is we take a family of sets and we union them all together. And you can think about it, I'm not going to prove this, but from this you can derive a partial order and prove that this join operation is the least, is a supremum operation, is the supremum operation for the partial order. And being a homomorphism, then well, in fact, before saying what a homomorphism is, with this, so this is now my definition of CSL. So CSL, hang on. Maybe I do want to say what a homomorphism is. So a homomorphism this is a join operation is a homomorphism if for every subset of X, H applied to the join of A is the join in X, of course, is the join in, well, it's just the same as before, isn't it? But so we have a category of complete semilattices and its morphisms, which I'm now calling homomorphisms. And we now hopefully see that this looks like a category of algebraic structures. And what I want to tell you now is that the complete semilattices enjoy the property that there's a free construction of a complete semilattice from a set. Can anyone guess what it is? So suppose we take a set and we want to sort of freely add joins to that set. So the set that we start off with doesn't have any order on it. So that's going to be sort of nothing there is going to be ordered. It's going to be like an anti-chain in the complete semilattice. But complete that into a partial order such that every subset has a join. Can anyone guess what that is? What the free way of doing that is? Okay, well, it's the power set of the set. So we consider the power set of a set. That's partially ordered by subset inclusion. And it's easy to see that that has joins, arbitrary joins, because if you take a family of subsets, the join is the union of those subsets. Okay, so a free algebra construction I don't want to underline it because there's not a definition here. Elucidating what it is, the free algebra construction for complete semilattices is power set. Let me just write power set. And in particular, let me write it as a proposition. We have forgetful as a left adjoint, but let's write that in the usual way we write that for free algebras. So for every set X and complete semilattice viewed in the new way, Y together with its join operation. So for every set X, complete semilattice Y with its join operation, and function f x to y, we want that this function extends to a unique homomorphism from the free algebra, so a unique homomorphism out of the power set. So that means there exists a unique homomorphism H from power set of X with as its complete semilattice structure, the union operation on it, to Y with its given join operation, such that this operation extends the function from X to Y in the following way. So we consider the diagram, the function f that takes X to Y. Well, we're generating the power set from X by considering the elements of X, their singletons, map the elements of X into the power set of X, and then we're then the unions freely adjoint to that. So this is the singleton operation. It doesn't, that's a curly right closed bracket there, doesn't look very good. So there's a unique homomorphism such that this diagram commutes. Okay. So in this case, we have a category that didn't particularly look like a category of algebraic structures, but it's not so far removed when we first looked at it. But we've shown that it is by giving a reformulation of it as a category of algebraic structures. And we've shown, moreover, that not only is it a category of algebraic structures, but we have a free such structure in the power set operation. Power set functor, if you like, is that it gives that free functor. So let me just write the alternative way of looking at it. I'll squeeze it at the bottom of the board here. So equivalently, equivalently, the forgetful functor from complete semi-lattices to sets has power set function functor from set to complete semi-lattices, which maps. I won't bother writing doing the actional morphism, which maps x to the power set of x together with the union operation as its left adjoint. And the operation of morphisms is just the direct image function here. So this is one of the covariant power set functors that we considered earlier in the course. Okay, so we have, as I say, a category that didn't immediately look like a category of algebraic structures that nonetheless we can reformulate as a category of algebraic structures, and it has a left, and the forgetful has a left adjoint, so that's like a free algebra functor.
And the U is a supremum or a union?
Sorry, this U is the union. Well, it's a cup, it's not a U. My U's have a little like this one, but anyway, this is a big cup operation. This is the union operation, but it is a supremum because the union operation is the supremum operation in the power set lattice. Right, where the derived order is subset inclusion. So while I'm erasing the boards, just to say, one can look at other kinds of algebraic structures that are similar, where one doesn't have fixed derivatives for the operations, but similar kind of complicated domains for the operations. And you don't always have a free algebra structure. So a very related category is the category of what are called complete Boolean algebras. Those are complete semi-lattices where the lattice is also what's called a Boolean algebra. If you don't know what a Boolean algebra is, it doesn't matter. And it turns out that the forgetful from the category of complete Boolean algebras to sets does not have a left adjoint. So the existence, whereas when you're dealing with algebraic structures where you've got a set of operations, each of which has a fixed-arity, but the existence of a left adjoint is guaranteed. Now we're looking at the kind of algebraic structure we're looking at with complete semi-lattices. The existence of a left adjoint is not guaranteed, but in the case of complete semi-lattices, one has one. But similar kinds of algebraic structures don't necessarily have free algebra functors. Okay, so I've looked at two of my examples. The third example is very different in the sense that it doesn't look like a category of algebraic structures at all. For the third example, I'm going to use the standard German notation for it. This is the category, the category of compact Hausdorff spaces. And continuous functions. So the category of topological spaces has been one of our running examples throughout the course. Compact Hausdorff spaces are topological spaces that are Hausdorff, that is enjoyed by people who prefer numbers, that is, they enjoy the T2 separation condition, and are moreover compact. Now, if you don't know all the general topology for this, then you just need to sort of just enjoy this section or not at a sort of impressionistic view, but probably most of you do. So just hands up if you know what a compact Hausdorff space is anyway. Yeah, okay, so everybody in the room at least knows what we're talking about. So this does not look like a category of algebraic structures at all. It's a category of topological spaces and continuous functions. So with the category of topological spaces, the forgetful from the category of topological spaces to sets does have a left adjoint. That's just the set X that maps the set X to the discrete topology on the set X. So all subsets are open. It also has a right adjoint. That's mapping a set X to a very uninteresting topology, the indiscrete topology. One could make jokes about the word indiscrete here, but I don't want to spend time on it. So the indiscrete topology has only two open sets, the whole set and the empty set. So it's a very uninteresting topology. But anyway, that forgetful functor has both a left and right adjoint. But it's not like a category of algebraic structures in the sense that we'll see the sense in which it's not like a category of algebraic structures. On the other hand, when you look at compact Hausdorff spaces, so you restrict to very well-behaved spaces, they're Hausdorff and they're compact, it turns out to actually be a category of algebraic structures. We can describe it in an equivalent way as a category of sets equipped with some operations, satisfying some equations, and morphisms as functions preserving those operations. Now, that's not an obvious fact at all. And to address this, we're going to look at two deep category theoretic results, which will give us this. Plus, we'll look at some general category theoretic machinery associated with algebras. The first deep result is we're going to show that the forgetful functor from compact Hausdorff spaces to topological spaces has a left adjoint. So for any set X, this is true. But we're only going to do it to the category of sets has a left adjoint. So for any set, you can find a free compact Hausdorff space over the set. You can't use the discrete topology anymore because if you've got an infinite set, the discrete topology is not going to be compact. So does anyone know this, by the way, how to construct this? Okay, so I mean, just in case you've seen related things, you can actually find a left adjoint from the forgetful from compact Hausdorff spaces to topological spaces. So you can turn any topological space into a compact Hausdorff space, and that's called the Stone-Check compactification of a topological space. And then you can, if you want, compose that with the left adjoint for the category for the forgetful functor from topological spaces to sets, and that gives you the left adjoint for the whole composite. Alternatively, you can construct this directly by forming a topological space on what's called the set of ultrafilters over the set X, and that gives you a compact Hausdorff topology here. So these are explicit constructions. These are fussy. So the way I'm going to do it is I'm going to show we've got a left adjoint without explicitly constructing it. And I'm doing that in order to introduce you to some powerful category theoretic terminology, which is powerful category theoretic machinery known as the adjoint functor theorems. What we're going to use is Freyd's adjoint functor theorem. Which we can abbreviate to FAFT. And sometimes, so it's due to Peter Freyd, and sometimes people just call it the adjoint functor theorem. There are several adjoint functor theorems, but this is kind of the most famous of the adjoint functor theorems. But most of the adjoint functor theorems are due to Freyd, so the use of Peter Freyd doesn't really distinguish between them. But just there are some references in the notes, so I recommend you look up in category theoretic books, you read about adjoint functor theorems for that interesting reading. We're just going to use one, and that's the following. So a functor G from a category D to a category C Actually, sorry, let me start again. So suppose D is a complete category. So in other words, it has limits, category, limits for all small diagrams. And suppose G from D to C reserves limits. Now we know that's a necessary condition for G to have a left adjoint, that it preserves limits. So right adjoints always preserve limits. So what in addition do we need for G to have a left adjoint? So then G has a left adjoint if and only if the following is satisfied. And this is called the solution set condition. And it says, for any object X in C, there exists a set I and I index family let me just check in my notes what I called them. Yeah, G sub I. Maps out of X into images of objects from D under the functor G. So this is a family of maps in C, such that for every map of the form X, F, G, Y, notice you're seeing something. This is one side of the isomorphism for an adjunction here, maps into the right adjoint. There exists an I, an index I, little I, such that the morphism F factors as G of H composed with G sub I for some H well, H here goes from Y sub I to Y in D. Okay, so notice GI takes us from H to G of YI, and G of H then takes us from G of YI to G of Y. Now, I'm not going to prove this, but I'll just make some remark about the proof of this. We're constructing a left adjoint, which is sort of like a co-limiting kind of thing to do, but our assumption is not to do with co-limits, it's to do with limits. We've got a complete category, that's D has arbitrary limits, and we know something nice about the functor G, that it preserves limits. Considering maps of this form, you can see it's related to adjunctions, but actually there's a very natural category called the comma category, whose objects are maps of this form out of X, and whose morphisms are sort of have this form, they're maps in D. And you can show that if G has a left adjoint, f of X is essentially determined by the initial object in this comma category. So if this comma category has an initial object, then that will determine the left adjoint on the object X. Now we don't have co-limits, we have limits. So how an initial object is a kind of co-limiting thing, but by a very similar but more involved, because it's a category theoretic version rather than a partial order version, by a very similar idea to the idea that allowed us to reduce infima impartial orders to suprema impartial orders. An infimum was the supremum of all lower bounds. A similar idea allows us to use limits to find an initial object as essentially the limit of all objects. But it's not all objects, but it's all objects in the set index family. To make it a small thing, we take a limit of. So that's a kind of high-level description of the ideas behind the proof. It's a very beautiful proof in my mind, and it gives us this nice condition. Now, we're already at break time, but what I would like to do is, I've written it out in detail, but I don't think I want to go through the details in the lecture. So I just want to spend 2 or 3 minutes giving you, again, a high-level idea of why this forgetful functor from compact Hausdorff spaces to set has a left adjoint. So we're going to apply this adjoint functor theorem. So the first thing is we need to show that compact Hausdorff spaces is a complete category, and that the forgetful functor preserves limits.
I'm sorry, Professor, but you didn't really turn the camera.
I didn't. Well, I pressed the button. Okay. Right. Maybe I pressed the wrong button. I thought I'd done it. So what we're going to prove is that compact Hausdorff spaces is complete, and well, in fact, rather than proving that the forgetful functor preserves limits, I'm going to prove that it does something even stronger, it's stronger given that the category of set is complete, and it does something that are called creating limits, which, there's a definition in the notes. I think I shall instantiate the definition just through giving the proof and telling you what I'm establishing. Okay. And I'm just going to do so limits can be reduced to products and equalizers, and I'm just going to do the example of products. So what we've got is we've got some family. So I'll be a bit fussy, and I'll say I'm going to consider the compact Hausdorff space together with its explicitly written topology on it. So tau I is the compact Hausdorff topology. And we want to find a product of this family of compact Hausdorff spaces. Okay, so that's not difficult because we have the topological product. And then we've got the projection functions down here. And Tikhonov's theorem tells us that the topological product of compact spaces is a compact space. There's a famous theorem in topology that tells us that. The axiom of choice is used. The axiom of choice is actually equivalent to Tikhonov's theorem in its full generality. The statement just for compact Hausdorff spaces, the statement just in the case of Hausdorff spaces, that the product preserves compactness is a bit weaker than the axiom of choice, but nonetheless, you need some form of choice to get it. Anyway, we'll have choice, and we have the product topology. It's compact. It's a compact Hausdorff space by Tikhonov's theorem. Well, actually, we can see that the forgetful functor to set preserves this limit because this is a topology over the set theoretic product. So in set we've got, so this is K house. Here we've got set. Here we've got the forgetful functor. But what does creating limits mean? So I've kind of actually done everything I need for the adjoint functor theorem already for the preserving limits. But anyway, I want to prove that it creates limits because this is a very nice proper feature of categories of algebras, something that categories of algebras enjoy that general categories with the junctions don't enjoy. And what creating the limits means is that this limit's not only preserved by the functor to set, but it's actually uniquely determined by the functor to set. And to say that, what we say is that if we're given any cone in set for this, sorry, any limit cone in set for this diagram, so any product, so any other product cone in set, there is a unique way of topologizing this product cone with a compact Hausdorff topology in compact Hausdorff spaces. So any limit cone here is the image of a unique cone up here. And moreover, that unique cone up here is a limit cone.
I'm sorry, what's the PI on the right side?
Right, sorry, this is just the cone.
No, not the pi.
The X is missing.
Oh, right, yeah, the X. That's the that's the product of, this is the product in sets of the set xi. But suppose we're given another product cone in sets. Well, then we have an isomorphism bijection in sets here. And that isomorphism, we've got the product topology here. We can just transport the topology on the isomorphism, and that gives us, of course, a compact Hausdorff topology here, which makes I into a homeomorphism. And that's the unique topology we can put on that's the unique compact Hausdorff topology we can put on that makes these maps continuous, because any other topology would have to have more open, at least as many opens, in order to make the projection maps continuous. So it'd have to be finer than the compact Hausdorff topology given by the product topology. But in a compact Hausdorff space, you cannot refine a topology, you cannot make a topology any finer and maintain the property of compactness. That's a very well-known fact about compact Hausdorff spaces. Once you've got a compact Hausdorff topology on the space, it's kind of, once you've got that, any finer topology won't be compact, and any coarser topology also won't be compact. So we've got this unique product cone living in compact Hausdorff spaces over the existing product cone here. Okay. So then there's the solution set condition, which I want to do other things in the second part. So that's in the notes. The idea here, to prove the solution set condition, we start off, so here we're going to start off with a set X and a map into the image of some compact Hausdorff space. And we want to show that any such map factors via continuous functions through maps into some set determined by X, some set of compact Hausdorff spaces. So we want to find some set of compact Hausdorff spaces into which any map from X into a compact Hausdorff space can factor through one of those. And the way to do it is to view that maps out of X into compact Hausdorff spaces. If we look at such compact Hausdorff spaces in which the image is dense, there are up to homeomorphism only set many of those. And whenever you have a map from X into a compact Hausdorff space, you can factor it through. You simply take the closure of the image in here and you factor it through another space in which the image is dense. So that's the idea. I realize that I'm omitting lots of details, but anyway, they're covered in the notes. And in the next part, I want to then go back to abstract material. So compact Hausdorff spaces are a little bit complicated to deal with, and I do want to focus more on the category theory, but I do want to give you at the same time a feeling for the kind of powerful technology that category theory provides that allows us to understand properties of more interesting examples like the category of compact Hausdorff spaces. Okay, so we'll have the break now. I'm afraid I'm going to just have the break until 20 past. I'm sorry, this is a rather intense lecture today, but the material will go back to more axiomatic material after the break.